Today, we're taking on a pretty critical mission. We're doing an intellectual excavation, really, into the foundations of our modern infrastructure. We're not just summarizing research here. We're trying to piece together the actual blueprint for, well, what might be the most complex technological achievement of the next decade. We're talking about building the artificial intelligence, the brain, for a working smart grid.
That's exactly it. And when we say brain, we're not being literal, of course. What we mean is identifying the essential frameworks, the behavioral insights, and the deep computational tools you need. All of it is required to let a massive distributed electrical network actually think and predict and adapt. So this deep dive is really your roadmap for understanding that transition. You're moving the grid from a simple, predictable physics problem to a dynamic, almost living ecosystem.
So if you're prepping for a high-stakes meeting, or maybe you're just trying to get your head around this intersection of complexity theory and power engineering, or if you just want to know what makes a smart grid genuinely smart, then you are in the right place. We've synthesized a whole stack of sources to pull out what we think are the 4 foundational pillars for this whole transition.
Right. We're going to start at the highest level of abstraction, the philosophical pivot. We have to redefine the smart grid as what's called a complex adaptive system, or CAAS. That part is, well, it's non-negotiable.
Okay, and then from there we tackle the human factor, which is huge. If the grid is so complex, how do we even design an effective collaboration between humans and machines? We'll get into this concept of adaptive autonomy, the system knowing when to step in and when to back off.
And then we bring all that high-level theory right down to earth.
Yeah.
Sort of mud on the boots reality check. We're going to walk through a real-world MLOps case study on predicting failures, and we'll see why something called feature engineering is really the key to building trust in the AI.
And finally, we zoom right in, past the weekly aggregated data down to the instantaneous pulse of the network. We'll explore how chaos theory and time series analysis let us essentially read the system's unique fingerprint at the millisecond level. It's a big journey, so let's get into it.
Yeah, let's start with the basics. I mean, for over a century, the grid was just a masterpiece of centralized, deterministic engineering. Analogies really help here. The traditional grid was like a simple one-way street.
Okay.
Power was generated at these huge centralized plants. It flowed one direction down transmission lines, and then it was consumed at the endpoints. The control was completely centralized, managed by a handful of operators following these rigid, predictable physics equations.
Simple, reliable, but totally non-adaptive.
Precisely. The smart grid, on the other hand, is, well, it's a dense, bustling, crowded, and super reactive ecosystem. It's not a one-way street anymore. Now you've got decentralized two-way generation. Think about massive solar farms, sure, but also thousands of individual rooftop solar arrays injecting power back into the grid at completely random points.
And the consumer isn't passive anymore, which is a huge change.
That is the crucial point. Consumers are now active participants. They're changing their consumption based on dynamic pricing signals. So if the price spikes at 4 p.m., a big industrial user might scale back production, or you might delay charging your electric vehicle at home. This introduces just massive variability. And then layered on top of all of that is a flood of sensor data and AI algorithms making real-time micro-decisions.
So the system is no longer just about the physics of voltage and current. Now you have to factor in market economics, the performance of the telecom network, and the unpredictable psychology of human behavior. And this is why we need that heavy term, complex adaptive systems. Why is that specific philosophical lens so vital?
Because it changes everything. I mean, everything about how we approach modeling, control, and prediction. The first pillar of CAS is that the grid is not a single entity. It's a system of systems.
Right. We said it's independent entities working together. So the power network itself, the communication network. What else falls under that umbrella?
You have to include the energy market. So the whole structure of pricing, bidding, regulation. And then there's the socio-technical system of human operators and millions of consumers. Each of these systems has its own dynamics, its own goals. The physics network wants stability, the market wants efficiency, the consumers want low prices, and they are constantly interacting, often in conflicting ways.
Okay, so why is that interaction inherently complex? In engineering, complexity usually just means lots of parts, but this sounds like it's something deeper.
You've hit the core distinction. Complexity here isn't about counting the components. It's defined by the nonlinear interactions between them. And nonlinear means that proportionality just breaks down. So I can apply a tiny little stress to the system, and the reaction could be disproportionately huge.
So it's not just that 2 + 2 doesn't equal 4, it's that it might catastrophically equal -10.
That's the consequence, exactly. For example, a tiny voltage fluctuation, I'm talking less than 1%, in one small area might, through a chain of nonlinear power flow reactions and relay trips, cause frequency instability across an entire country. The small cause had a massive, unpredictable effect. Simple models just can't capture that.
And this unpredictability leads right to the defining feature of a CIS, emergent behavior. Can you walk us through that classic example, the cascading failure, but really focus on the emergence aspect?
Absolutely. Think about the big blackouts you hear about. The initial failure is often trivial. Could be a single piece of equipment overheating or a small software bug that trips one minor transmission line. A very local, simple failure.
But somehow the system coordinates a disaster from that.
It finds a way. The load that was on that failed line has to go somewhere, so it instantaneously shifts to the lines next to it. But those adjacent lines, they weren't designed for that sudden spike, so they overheat, hit their limits, and they trip off too. And this domino effect just propagates incredibly fast across state and even national borders, leading to a total system collapse. No single person ordered this blackout. The failure was a spontaneous, unintended, system-wide behavior that emerged just from the local interaction rules between the components.
So emergent behavior is the system organizing itself toward a goal, even a catastrophic one, without any central director. You called it a conspiracy without a conspirator.
It's the perfect way to put it. And the flip side of that, the thing that gives us hope for building this brain, is self-organization.
That seems a little counterintuitive. If the system is that fragile, how does it organize itself?
Well, look at biology. A flock of birds, a school of fish. They move with this perfect fluid coordination, but there's no leader. They're all just following a few simple local rules. Stay this far from your neighbor, match the speed of the birds right next to you. And that incredible global structure, the beautiful shape of the flock, that's a self-organized pattern.
So what does that look like in the grid, practically speaking?
We actually see it in crises. You see this spontaneous adaptive behavior from human operators. When they're faced with a totally new scenario, something that's never been seen before, operators often develop these unwritten, intuitive procedures in real time to pull the system back from the brink. These procedures aren't in any manual. They're a kind of collective, spontaneous intelligence, a temporary self-organization that emerges under extreme stress. And the sources argue that we have to understand that behavior if we ever hope to program it into an AI.
Which brings us to the big realization then. Because the smart grid is a CAS, trying to model it with classical textbook physics equations it's doomed to fail. We can predict how any single component behaves, but we can't predict the nonlinear sum of all their interactions.
That is the core takeaway for anyone developing this AI. You need new tools. You need concepts from information theory, from complexity science, from data analytics tools that are specifically designed to capture the pulse of this living, self-organizing entity.
Okay, that philosophical shift is profound, but it poses a huge challenge for our next section. If the network can self-organize and we're building an AI that can predict and adapt, doesn't that sort of imply we should just get out of the way? I mean, why build a complex management AI if the system will just heal itself like a flock of birds? Is the human operator going to become obsolete? Just a spectator?
That is probably the most challenging and, frankly, ethical question in this whole discussion. And the research is very clear on this. The human operator is not going to be eliminated. Their role has to fundamentally change. And what's more, the interaction itself, the one between the operator and the automation, is also a complex adaptive system.
The collaboration itself is a CAS. Okay, talk me through that feedback loop.
Think of it like a continuous high-speed dance. The operator makes a decision, right? Let's say they divert power flow. That action instantly affects the grid. The new grid status is then processed by the AI and shown on the monitor, and that display could show a successful stabilization or the crisis getting worse. That data, appearing under high stress, immediately affects the operator's mental state, their stress levels, their cognitive load, their trust in the machine, and all of that profoundly influences their very next decision.
Wow. So the performance of the entire grid depends as much on the psychological state of the human as it does on the physical state of the wires. If the AI does something confusing, it increases human stress, which leads to worse decisions, which leads to worse grid stability. It's a vicious cycle.
Exactly. So the goal isn't to eliminate the human, it's to design a resilient partnership. And the sources call this adaptive autonomy.
Adaptive autonomy. That suggests the level of machine involvement isn't fixed, it's variable.
It has to be variable and intelligently so. The system needs to be smart enough to look at real-time conditions and decide When should the AI take total control? Because it can run millions of calculations faster than any human. And just as important, when should it pull back and handful immediate control to the human because the situation requires an intuitive judgment that algorithms just don't have yet?
So what determines that level of autonomy? What are the key variables the system is looking at to make that handoff decision?
The researchers call them performance shaping factors, or PSFs. These are the situational variables that determine the right level of machine involvement.
Can you give us some concrete examples? In a control room, what would a PSF be?
Okay, so on a routine, calm, day-low load, all equipment is working perfectly. The PSFs indicate low risk. The system can run at, say, autonomy level 4. It handles mundane tasks, which reduces the cognitive load on the human operator. Now, contrast that with a situation where 3 PSFs combine. 1, the weather forecast shows an 85% chance of a severe storm hitting a key substation. 2, protective equipment in that same area is flagged as being past its mean time between failure. And 3, the operator is in the last hour of a really demanding 12-hour shift.
Okay, so the system sees multiple indicators, all pointing to high risk, high uncertainty, and potential human fatigue.
Precisely. And under those combined PSFs, the system has to recognize that this situation requires context and human intuition. So it automatically reduces the autonomy level from 4 down to 2 or 1, and it transfers full control and responsibility back to the operator's console.
But how do you program that? That seems incredibly complex, this state-dependent decision-making. This is where the sources brought up a tool called Petri nets. We should probably explain that a bit more. It's more than just a smart flowchart, right?
Oh, much more. Petri nets are a mathematical modeling tool. They're used a lot in designing complex distributed systems because they explicitly model things like concurrency, synchronization, and resource availability, all critical for a grid control room. They have 4 core elements. You have places, transitions, arcs, and tokens.
Okay, that sounds dense, but let's break it down.
Right. Think of places as the states of the system. For example, autonomy level 4 is active, or storm probability is greater than 80%. Transitions are the events or the rules that trigger a change in state, like receive new weather data. And tokens represent the resources or the conditions that are available. A token might be the actual data confirming that storm, or the time that's passed since the last system check.
So to get from one state or one place to another, a specific transition has to fire.
Exactly. And a transition can only fire when it has the right tokens in its input places. This structure is what makes it so powerful. First, it means you respect resource constraints. You can't act if you don't have the data token. And second, it lets you verify that the model is deadlock-free. You can prove that the human and the machine won't get stuck waiting for each other to act.
Could you walk us through that storm scenario again, but using that language of places and transitions?
Sure. So imagine you have a transition called transfer control, and you have 2 places feeding into it. Place A will get a token if the equipment age PSF is high, meaning you have old equipment. Place B gets a token if the weather risk PSF is high. Now, the transition transfer control is programmed to fire only if there are tokens in both place A and place B.
So unless the storm risk and the equipment risk are high at the same time, the system just stays at its high autonomy level.
Correct. But once both those tokens arrive, the transition fires. That starts a sequence that removes the token from the autonomy level 4 state and places a new token in the autonomy level 2 state. At the same time, it triggers the transfer of display permissions and control authority to the human console. It's that mathematical rigor that makes the whole thing trustworthy and verifiable.
What this proves is that you're building a whole management system on top of the control system just to manage the collaboration. So everything down to the psychology of intervention, it all has to be data-driven and mathematically modeled.
It's the ultimate expression of that CACF philosophy, but now applied to human factors. You have to collect data on the conditions where humans and machines perform best together, just so you can program the rules for the Petri net.
That is incredibly detailed. Okay, so let's pull this abstract theory down into a concrete application. Has anyone actually built a tangible piece of this grid brain using these ideas?
They absolutely have. One critical study looked at building a predictive module. The goal was to forecast the weekly number of equipment failures in what are called medium voltage feeders. These are the lines that bring power from substations into your neighborhoods and businesses.
So this is a total shift. We're moving from theoretical physics to messy, real-world data science. Maintenance logs, equipment models, repair schedules, local weather data.
And the operational goal is huge. You're translating all that raw historical data into actionable intelligence. Imagine being the network manager and getting an alert that says, expect 12 failures on feeder A and 8 on feeder B next week. Get your repair teams ready. That kind of predictive power dramatically reduces outage times and saves a lot of money.
And the success of a model like that really hinges on the most time-consuming and critical part of the whole process, which the sources call the gold rush phase, feature engineering. Why is this one stage so much more important than just picking some fancy machine learning algorithm?
Because in complex systems like the grid, the problem isn't the algorithm. It's the sheer volume of noisy, high-dimensional data. Machine learning models are, at their core, just very effective pattern finders. If you feed them irrelevant data, they'll find patterns, but those patterns will be meaningless noise. Feature engineering is the art and science of sifting through all that data to find the true underlying signals, the features, that genuinely predict the future.
So you're looking at things like equipment age, recent maintenance, maybe peak loads, local temperature records. How did they deal with the diversity of all that information?
Well, the core insight, and this echoes our CAS discussion, was that no single technique works well enough. The interactions are nonlinear, so they had to use a diverse analytical toolbox.
Let's break down that toolbox. The simplest one is just simple correlation analysis. What are its limitations here?
Correlation is fast. It's easy, but it only finds linear relationships. It's good for saying older equipment correlates with more failures. But what if the failure requires a combination of high humidity and high temperature? Correlation will probably miss that because neither humidity nor temperature alone might correlate that strongly with the failure.
Okay, so how did they capture that more complex nonlinear dependency?
They move to more advanced techniques, like mutual information. Mutual information comes from information theory. It measures the dependence between two variables by asking how much knowing one reduces your uncertainty about the other. And crucially, it captures both linear and nonlinear dependencies. So it would be the tool that successfully identifies that the combination of high humidity and peak current load is a powerful predictor for cable failure, even if each variable on its own was a weak signal.
That is a critical distinction. You're looking at information flow, not just linearity. What about the third major technique they mentioned, lasso? Why do you need a specialized regression model on top of these other tools?
A lasso, which stands for Least Absolute Shrinkage and Selection Operator, does two things that are critical for grid data. First, it performs feature selection while it's fitting the model. Grid datasets can have thousands of potential features. You can't test all the combinations manually. Lasso aggressively drives the coefficients of irrelevant features down to zero, effectively cutting them out of the model for you.
So it's a filter and a fitter all in one.
Exactly. And second, it uses regularization. It adds a penalty based on the size of the coefficients. This forces the model to prefer simpler explanations over overly complex ones, which helps it generalize to new data much better. In a real-time system, Lasso gives you a smaller, more robust set of high-impact features, which drastically cuts down on computation time.
This detailed process just reveals the gold standard of AI development, doesn't it? The intelligence is really in the data prep, not just the model you choose. Now, when they looked at the results, the paper stressed that good feature engineering didn't just boost accuracy. It dramatically reduced something called the relative generalization gap, or RGG. Let's define that. Why is reducing it so critical for building trust?
The relative generalization gap, the RGG, is a metric that measures the difference in a model's performance between the training data, the historical data it learned from, and its performance on a completely unseen test set new data it's never encountered before.
So it's a direct measure of overfitting.
It is the direct measure of overfitting, yeah.
Yep.
A large RGG means your model is a genius at memorizing past failures, but is terrible at predicting future ones.
Let's use that student analogy again. A student scores a perfect 100 on all the practice exams, but then gets a 50 on the final.
The gap between that 100 and the 50 is the generalization gap. A high RGG tells the grid manager, your model is a memorizer, not a learner. You can't trust it for real-time operations. Good feature engineering, by feeding the model only the fundamental drivers of failure, forces the model to actually learn the underlying physical rules, rather than just memorizing the noise in your historical data.
So reducing the RGG is the ultimate proof that the AI is safe to deploy. It means the model will give you stable, reliable predictions on new data, which is the only data that matters when you're scheduling repair crews for next week.
It's what separates an academic prototype from a robust industrial solution.
This has all been about aggregated, weekly data predicting the volume of failures next week. But the smart grid is a dynamical system with variables changing every millisecond. So we need to shift our focus now from weekly prediction to the instantaneous pulse of the network. This is where we zoom into the micro level, into time series data and the idea of chaos.
That's the perfect transition. Yeah, up to now, we've been dealing with big aggregated numbers. Now we're looking at voltage, frequency, and current waveforms that are recorded thousands of times a second, these continuous measurements. This is our time series data.
And the core question changes completely here. We're not asking how many failures next week. We're asking, what is the true nature of this tiny fluctuation right now? Is it just random, meaningless noise? Is it simple, predictable, periodic behavior? Or is it something else, something we can define mathematically as chaos?
And that diagnosis noise versus chaos is absolutely essential because it dictates your entire control strategy. If a system is purely random, prediction is impossible. If it's periodic, prediction is trivial. But if it's truly chaotic, that means the system is deterministic, but it's exquisitely sensitive to initial conditions. Long-term prediction is impossible, but short-term prediction is achievable.
Can you give us that medical analogy again, but with a bit more on the control implication?
Sure. Imagine a heart arrhythmia signal. If a cardiologist decides the fluctuations are just simple noise, they might ignore them. If they're periodic, they can be treated easily. But if that signal is coming from a deeply chaotic process, the doctor has to use a nonlinear control strategy. If you try to fix a chaotic system with a simple, small correction, a gentle nudge, you can actually push the system exponentially faster toward a worse state. The control has to respect the chaotic nature of the physics.
So in the grid, if the power output from a big battery system or a wind farm is chaotic, our predictive models and our control algorithms have to be designed to handle that sensitivity. Trying to dampen a chaotic frequency fluctuation with a simple controller might just catastrophically amplify it.
Exactly. You need to know what you're dealing with. You have to distinguish the true underlying process, the subtle signature of a potential collapse, from all the surface noise.
And this is where we connect our earlier discussion of macro-level complexity, self-organization, and emergence to this micro-level time series data. The research says we should treat time series not just as numbers, but as the fingerprint of the entire complex adaptive system.
This is maybe the most profound conceptual leap in all the research. The idea is that the systemic state of the CAS, whether it's stable or self-organizing or heading towards a catastrophic failure, that state leaves a tangible signature, a hidden structure embedded in the millisecond fluctuations of the voltage and current waveforms. The macro dictates the pattern of the micro.
So if a group of operators is spontaneously self-organizing to avert a crisis, or if a slow, nonlinear instability is building up across the whole system, that process is somehow reflected in the complexity of the signal on the screen.
Precisely. And the challenge then is, how do we mathematically extract those systemic features from the raw data? The research identifies 4 key emergent features that you can extract directly from the time series. First is complexity. How intricate is the signal? You can measure this with things like sample entropy. A highly complex signal often indicates a healthy, adaptable system. A signal that suddenly simplifies could mean the system is locking into a dangerous state.
Okay, complexity is one. What's next?
Second is self-organization. How much structure has the system built for itself? This is quantified by looking for local patterns or correlations that persist over time. Third is emergence. Is there macro behavior subtly encoded in there? This uses specialized stats to see if the system is starting to show long-range dependency, which is a known precursor to large-scale events. And fourth is predictability. How forecastable is this behavior? This is where you use classic chaos theory metrics like the largest Lyapunov exponent, which confirms chaos and tells you your time horizon for accurate prediction.
That's incredible context. So you're not just calculating simple statistics. You're asking the signal, how structurally sound are you and how close are you to chaos? You're characterizing the system's health using attributes from the very definition of CAS.
Exactly. And the exciting result from the initial paper was that these 4 emergent features, even when you use them as inputs for pretty simple classifiers like an SVM or KNN, they could already distinguish between chaotic and non-chaotic time series with remarkably high accuracy.
And having that success with established, simpler models must have given them huge confidence in the whole philosophy. It means the features themselves are doing the heavy lifting.
They are. The features are the key. And this understanding really sets the stage for the next generation of AI. The source mentions follow-up work, where when you embed this philosophy, this explicit representation of complexity and self-organization, directly into the architecture of a deep neural network, the accuracy jumps to near 99.5%. That is a powerful validation of translating complex systems theory directly into code.
This has been a really comprehensive journey. We've moved from the highest theoretical plane all the way down to the lowest millisecond level of data.
We really have. We've covered 4 critical shifts you need to build the smart grid's brain. First, that necessary philosophical pivot. Seeing the grid not as a machine, but as a complex adaptive system defined by nonlinear emergent interactions.
Right. And second, we moved to human factors. We saw that the AI has to be a trustworthy partner, which requires designing adaptive autonomy using sophisticated tools like Petri nets to manage that loop between human psychology and the system's state.
Third, we grounded all that theory. We dissected a real MLOps pipeline for predictive maintenance, and we emphasized why robust feature engineering and minimizing that relative generalization gap are the absolute keys to building a model you can trust.
And finally, we realized that the key to millisecond control is treating time series data as the system's fingerprint. That allows us to extract emergent features like complexity and predictability to diagnose what's really going on.
This whole analysis really provides the perfect context for future deep dives. We touched on measuring complexity, but the future of this research leans heavily into things like Joint-Entropy. It's an advanced tool for quantifying the information flow between different parts of the grid, say, between a solar farm's output and a local substation's load. Understanding that is crucial for really predicting macro emergence.
Hopefully this conversation has given you a clear, actionable roadmap for navigating this incredibly dense field. But before we wrap up, let's leave you with one final thought. The ultimate challenge that's implied by all of this work.
We established a pretty profound principle today. A complex system's macro behavior leaves a recognizable, quantifiable signature on its micro-level time series data. The fingerprint of a collapse is visible in the voltage spikes before it happens.
The system tells you what it's about to do.
So the provocative question is the inverse of that. Can we reverse the process? If we can measure the emergent features in the time series, can we use those features as targets for control?
You mean instead of just reacting to the complexity, we could proactively structure it?
Exactly. By deliberately engineering the time series at the micro level, by structuring their complexity, their self-organization, their predictability, using very fast-acting controllers, can we purposefully induce desired macro-level emergent behaviors, things like ultra-resilience, systemic stability, or even robust self-healing within the smart grid. That is the ultimate goal of leveraging complexity theory. Not just observing chaos, but actively engineering reliable order.
And that is the ultimate goal of the AI brain, to become a masterful conductor of complexity. Thank you for joining us for this deep dive. We'll catch you next time.
So our last conversation, we really got into the weeds, didn't we? We were talking about the machinery of modern machine learning.
We were deep in feature engineering pipelines, MLOps, especially for, really sensitive industrial stuff like smart grids.
Exactly, the whole system infrastructure.
Right.
But today, I think we need to take a step back, a really fundamental step back, away from the toolkit, away from the models, and look at the raw material, the actual data itself.
Signal.
The time series signal. Before we can even think about building the perfect model, we have to, understand the language the data is speaking.
And that is the absolute core of it. What is the fundamental nature of this thing we're trying to model? Is it clockwork, perfectly periodic and predictable?
Like a metronome?
Right. Or is it just pure static, white noise, completely random, with absolutely no pattern defined?
Or is that third thing, that really strange, fascinating middle ground that physics calls deterministic chaos?
And that's our mission today, because that thin line between what looks like chaos and what is genuinely random, well, it's almost invisible to the naked eye.
But the sources we've looked at today, they make a really powerful case that seeing that line, that distinction, can be the difference between, operational success and just catastrophic failure.
So we've got two things on the agenda. First, we need to get into why this isn't just some, abstract academic debate. Distinguishing chaos from random noise has massive real-world stakes in medicine, in energy, you name it.
And second, we're going to dissect how these newer data-driven tools coming out of entropy and complexity theory have finally given us a way to, well, to decipher the hidden structure in these incredibly messy signals.
Let's do it.
Okay, so let's start right there with the definition. Because I think for most people, chaos just means a total mess, right? Absolute disorder. But when scientists say deterministic chaos, they mean something very, very specific.
They do, and it's the most important place to start because it's built on a paradox. At its absolute core, a chaotic system is completely deterministic.
Deterministic. Okay, so that means the outcome is, for all intents and purposes, fixed if you know the starting point.
Precisely. The rules it follows, the mathematical equations that govern the system, they are 100% specified. There's no coin flip, no random variable baked into the physics of it.
So in theory, if you could know the initial conditions with, what, infinite precision?
Then you could predict its future forever, theoretically.
But that's the paradox you mentioned, because in the real world, when you look at the output of these systems, it just looks like a mess. It looks completely erratic.
Statistically, it can be indistinguishable from pure randomness.
It's an illusion of randomness, then. An illusion that's actually coming from a system with a very rigid, ordered structure underneath.
That's a great way to put it. It's like a machine with these incredibly complex internal gears that follow ironclad laws, but on the outside, all you see is this dizzying, unpredictable pattern of movement.
So what's the engine for that? What's the mechanism that takes this internal, rigid order and creates this external, chaotic appearance?
It all comes down to one thing: an extreme sensitivity to initial conditions. This is, the bedrock idea of chaos theory.
The famous butterfly effect.
The butterfly effect. But let's really dig into what that means, not just as a metaphor. Imagine you're running two computer simulations of the exact same system, same deterministic equations.
Okay.
In simulation A, you set the starting temperature to, say, 20.000 with a bunch of zeros.
Right.
In simulation B, you set it to 20.000, and at the very end, a 1, a billionth of a percent difference.
A difference that, in the real world, is completely unavoidable. You could never measure something that precisely.
Never. And that tiny, immeasurable difference, it doesn't just cause a small proportional error down the line. It grows exponentially.
So it gets amplified.
Massively amplified. After just a few steps in the simulation, the path that simulation A is on and the path that simulation B is on, they will have completely wildly diverged. They start off almost touching, but they end up in totally different parts of the system space.
It's like the ultimate amplification system for any tiny measurement error.
And the classic example of this, the one that really kicked off the whole modern field, is the Lorentz system.
This is the weather model, right?
A very simplified one, yeah. Just 3 nonlinear equations meant to model convection in the atmosphere, and it showed exactly this behavior.
Which was a huge shock at the time, because the old Newtonian view was basically, if we just have enough computing power and we know the laws of physics, prediction is just a matter of time.
Exactly. Lorentz completely shattered that. He showed that even if you have a perfect model of the atmosphere, precise long-term weather forecasting is fundamentally impossible.
So it's not that our models are bad.
No. It's an inherent property of the system itself. We can never, ever measure the initial state, the temperature, the pressure, the humidity at every single point on Earth with the infinite precision you would need to stop that tiny initial error from ballooning and completely destroying your forecast after, say, a week or so.
That's a really profound idea. It says that for some systems, the limits on our ability to predict aren't technical, they're fundamental.
They are baked into the nature of reality for that system.
Okay, let me introduce one more concept here that I think is key. The strange attractor. Because if these systems are chaotic, they never repeat the exact same state, but they don't just, explode into infinity either, do they?
That's a vital point. Chaotic systems are bounded. Their behavior is incredibly complex, but it stays confined to a specific region of what we call phase space. And that region is the strange attractor.
What does that look like?
Well, it's infinitely complex. It has a fractal dimension, meaning it's more than a 2D surface, but not quite a 3D volume. But it's not just random wandering. The best analogy is a planet in a weird orbit. It's always tethered to its star. It never flies off into deep space.
Right.
But if its orbit were chaotic, it would never trace the exact same path twice. It would just keep drawing this infinitely intricate pattern within the gravitational pull of that star. There's order in its boundaries, but incredible complexity in its path.
Okay, so deterministic but unpredictable. Complex but bounded. I think we need to have that definition locked in before we move on.
Agreed.
Because now we get to the big question for you, the listener. Why should you care? In a practical, high-stakes scenario, what is the actual tangible difference between a signal that is truly random noise and one that is chaotic?
It's absolutely critical. I mean, it's not just a matter of choosing the right model. The entire operational strategy you would use to intervene in a system is completely different depending on the answer.
You can't treat them the same way.
Not at all. If you mistake a deterministic chaotic system for a random one, you miss this huge opportunity for intelligent control. And if you make the opposite mistake, if you think a random system has a hidden order, you end up betting the farm on models that are guaranteed to fail.
Let's make this concrete. The sources give some amazing examples. Let's start with the medical one. Cardiac arrhythmia.
Irregular heartbeat, yeah. Research into heart dynamics, especially what happens in the lead up to something catastrophic, like ventricular fibrillation, suggests that the heart's electrical system can enter this state that looks completely erratic.
Like just random noise.
To the naked eye, yes. But a lot of analysis has shown that in many cases, this isn't just noise, it's better modeled as a chaotic regime.
And chaos means there's a hidden deterministic structure underneath all that mess.
Exactly. And because it's chaotic, it has that extreme sensitivity we just talked about, and that sensitivity is actually something we can exploit. Well, if we correctly identify that the heart is in a state of deterministic chaos, the medical intervention can be incredibly delicate. You can use these techniques like pulse parameter modulation. These are the tiny targeted electrical flicks that were mentioned.
What does that actually do physically? A tiny
Because the system is so sensitive. A very small, very carefully timed electrical pulse, we're talking a tiny fraction of the energy of a full-on defibrillator, can be introduced at just the right moment in the cycle.
And that tiny pulse gets amplified by the system's own chaotic dynamics.
Precisely. It acts like a gentle nudge. It uses the system's own sensitivity against it to push it off that chaotic, strange attractor and guide it back toward a stable, periodic, healthy rhythm. It's an intelligent, low-energy form of control.
A gentle nudge compared to the alternative.
The alternative, which is what you have to do if you assume the behavior is just random noise, is high-energy defibrillation, a massive electric shock.
Paddles.
The paddles. It's the equivalent of hitting the power button off and on again, just trying to force a complete system reset. It's aggressive, it's traumatic for the patient, it's incredibly invasive.
So the diagnosis chaos versus noise literally determines whether the treatment is a gentle nudge or a lightning bolt to the chest.
It's that stark. It has a direct impact on patient outcome and long-term health. The distinction is absolutely vital.
Okay, let's switch gears to the energy example, which is less about life and death and more about, well, massive economic consequences. Forecasting power from a wind farm.
Wind power is notoriously spiky, right? It's all over the place. Now, if those fluctuations in wind speed and therefore the turbine output are truly random noise.
Meaning each data point has no connection to the last one.
Right. It's just a series of random events.
Right.
If that's the case, then any predictive model we build is basically useless beyond calculating an average. We can say, on average, we expect this much power, but that's it.
You have no idea about the sudden drops or the big spikes that are coming in the next few minutes.
None. And if you're a utility company, that means you have to be incredibly conservative. You have to maintain what's called spinning reserve.
What's that?
That's backup power plants, usually gas turbines, that are literally running spinning, but not connected to the grid. They're just sitting there burning fuel, ready to be switched on in an instant because you have zero confidence in the stability of your wind farm.
And that's expensive.
Hugely expensive. That reserve might be 20%, maybe even more of your grid's entire capacity. We're talking millions of dollars a year just to maintain that safety buffer.
Okay, but, and this is the core of it, what if those wind fluctuations aren't random? What if they're chaotic?
Now everything changes. If it's chaotic, it means there's a hidden deterministic structure. The system has memory. The current state has information about the future state.
It's not just a random walk.
It's not. And that hidden nonlinear structure can be learned by specialized predictive models. Now, we're not talking about predicting the wind a month from now. That's impossible.
Right, the butterfly effect.
But we can predict the short-term fluctuations with much, much greater confidence than if it were purely random. We can see the patterns in the chaos.
And what does that mean for the utility company and its spinning reserve?
If they can trust the model's short-term forecast, they can slash that spinning reserve, maybe from 20% down to, I don't know, 5 or 10%.
Which would save a fortune.
A fortune. And it improves grid efficiency. The wrong classification here either leads to massive wasted capital costs, or, in the worst-case scenario, if you assume stability that isn't there, you get blackouts.
Oh, so the dual risk is crystal clear. Mistake number one. You treat chaos like it's random noise. You lose the chance to predict and optimize, and you're forced into these expensive conservative buffers.
Right.
Mistake number two. You treat random noise like it's chaos. You put your faith in a model that's just fitting patterns in static, and it will inevitably fail, leading to operational collapse.
And that's why this isn't some academic puzzle. It's a daily operational requirement in financial markets, trying to model volatility. It's critical in earthquake analysis, looking for tiny precursors. It's everywhere.
Okay. The stakes are set. The problem is clear. How in the world do you actually tell the difference? Especially when you're dealing with messy, real-world data that's noisy and short?
Well, historically, the first attempts came straight from physics. The big theoretical tools.
The model-based methods.
Yes. The idea was to try and characterize the system's trajectory in that phase space we talked about. And the two most famous tools for this were calculating Lyapunov exponents and the fractal dimension.
Can you just quickly break down what each of those was trying to measure?
Sure. A Lyapunov exponent is essentially a number that measures the average rate at which two nearby paths in the system diverge from each other.
It's a direct measurement of the butterfly effect.
It is, yeah. A positive Lyapunov exponent is the classic textbook signature of chaos. If it's 0 or negative, the system is stable or periodic.
And the fractal dimension.
That was about measuring the complexity of the strange attractor itself. How intricately and densely does the system's path fill up its little corner of phase space? These are beautiful ideas in theory.
But in practice?
In practice, they had a fatal flaw. They really only worked on perfect, ideal data.
Simulated data from a computer.
Exactly. Data that was incredibly long. You needed thousands and thousands of data points, and most importantly, completely clean, totally noise-free.
And real-world data is never noise-free.
Never. The moment you introduce even a little bit of real-world measurement noise, it completely swamps the delicate geometric calculations that these methods rely on.
Why is that? How does the noise break it?
Well, think about the Lyapunov exponent. It's trying to measure exponential divergence caused by the system's dynamics. But noise, by its very nature, adds random divergence at every step. The calculation can't tell the difference between the two.
So it sees the noise and thinks, chaos.
Or it just produces garbage. And for the fractal dimension, the noise just smears out the fine, intricate structure of the attractor, making the measurement meaningless. It's like trying to measure the coastline of Britain during a blurry earthquake.
On top of that, these methods were also, I read, really sensitive to their own internal settings.
Hypersensitive. You could tweak one of the calculation parameters just a tiny bit and get a completely different answer. They were just too brittle for the real world.
And that failure, that brittleness, is what forced this big paradigm shift.
It was. We had to stop trying to reverse engineer the complete, beautiful mathematical model of the system from messy data. It was just too hard.
So instead, the focus shifted to something more practical, extracting meaningful, descriptive features directly from the signal itself.
We went from trying to find the equation to trying to find the signal's fingerprint.
And this shift opened up two really powerful parallel lines of research.
It did. One track came from information theory, using tools like entropy. The other track tried to find ways to directly quantify these, well, almost philosophical concepts from complexity theory, like self-organization.
And the amazing thing, which is the core of the sources we looked at, is that these two different streams, they eventually converged. They ended up telling the same story.
A really strong theoretical convergence that was then backed up by, well, overwhelming empirical results.
So let's dive into that first stream, entropy. We talked about it as a measure of surprise or uncertainty. A perfect sine wave has low entropy because it's predictable. White noise has high entropy because it's maximum surprise.
Right.
But the researchers quickly realized you couldn't just use one single type of entropy. Why not? What was it about chaos that required more than one lens?
Because chaos is, in a way, two things at once. It's highly ordered in one sense. It has these repeating structural patterns, but it's also highly disordered in another sense, which is the range and distribution of its values. You need two different rulers to measure those two different dimensions of its character.
So let's get specific. Let's break down the two most important complementary measures the research landed on. Start with permutation entropy, or PE.
Okay, permutation entropy is fascinating because it's a measure that is based entirely on structural order. It actually throws away the real values of the signal. It doesn't care if the temperature is 50 degrees or 100 degrees.
It ignores the quantity. So what does it look at?
It only cares about the relative ranking of a small sequence of data points. So it takes a small window of, say, 3 or 4 points, and it just asks, what is the shape? Is the sequence going up, up, up? Or is it up, down, up? Or maybe down, up, down?
So it's looking for the recurring motifs, the little patterns of peaks and troughs. You can almost say it's listening to the melody of the signal, not the specific notes.
That is a perfect analogy. It quantifies how often these little structural melodies repeat themselves. If a system has strong, repeatable internal rules that govern its shape, even if the actual values are all over the place, its permutation entropy will be relatively low.
Because the next little shape is fairly predictable.
Exactly. And this makes PE an incredibly powerful proxy for a core concept in complexity theory: self-organization.
The flock of birds.
The flock of birds. There's no leader, but the simple local rules create this highly organized, predictable macro pattern. The structure is ordered. PE measures that structure.
Okay, so that's one lens structure. Now, what's the other one? Distribution entropy or DE?
Distribution entropy is basically the opposite. It ignores the structure, the order of the points, and focuses entirely on the values themselves. The notes, to use your analogy.
So it's looking at the range of values the signal is hitting.
Exactly. It quantifies the statistical spread or dispersion of those values. Are all the signal's values clustered tightly around an average? Or are they scattered widely across the entire possible range? DE is highly sensitive to that statistical content.
And if the system is constantly producing wildly different values, jumping around a lot, its distribution entropy will be high.
It will. And this measure, it turns out, is an excellent proxy for the other major concept from complexity theory: emergent behavior.
Why that connection? What does the spread of values have to do with emergence?
Well, think about what emergence is. It's the appearance of a new large-scale pattern that you couldn't have predicted just by looking at the individual parts. When a system enters an emergent state, think of a sudden traffic jam forming, the system as a whole starts to occupy new states that were previously very rare.
The statistical distribution of car speeds suddenly changes. You get a big new peak at 0 miles per hour.
Precisely. The distribution widens or changes shape dramatically. Distribution entropy, by measuring that spread and that range of values, is incredibly effective at capturing the statistical signature of that emergence.
So we have our two lenses: PE for self-organization, the internal order, and DE for emergent behavior, the new macro patterns. But now we have the answer to the skeptical question. If one entropy measure on its own didn't really work, why did just adding a second one suddenly crack the whole problem open?
This is the absolute crux of the research, and it's a brilliant insight about, of all things, geometry, the feature space. The older methods that used a single entropy measure, like sample entropy, they kept hitting a wall because that single measure was, in effect, trying to measure both self-organization and emergence at the same time.
It was capturing a blend of the two concepts.
A blend, yes. And while those two concepts are theoretically distinct, in a lot of real-world signals, they happen to be highly correlated.
So when one goes up, the other tends to go up too.
Exactly. So what happened was when you took all your different signals, your random noise, your chaotic signals, your simple periodic signals, and you plotted them using that one entropy measure.
They all just fell onto a single line.
They all clustered along a single diagonal line in the feature space. The chaotic signals were mixed in with the noisy ones. You couldn't draw a clean boundary between them.
Which means any simple machine learning classifier would fail. It can't separate groups that are all jumbled together on a line.
They were statistically inseparable. The genius of the joint-entropy approach was realizing that by carefully choosing two complementary measures, PE for structure and DE for distribution, they could essentially force a statistical decorrelation.
They could break that link.
Yes. So when they plotted their results on a 2D graph, with permutation entropy on the x-axis and distribution entropy on the y-axis, suddenly it all snapped into focus.
What happened?
The chaotic signals moved into their own specific, distinct quadrant of the graph. The random noise signals moved to another. The periodic signals moved to a third. They were cleanly separated.
So by adding a second, carefully chosen dimension, they pulled the overlapping clusters apart.
They did. The theoretical distinction, self-organization versus emergence, was successfully translated into a geometric statistical separation in the feature space. It was a massive breakthrough.
A huge conceptual leap. And the results, I mean, the numbers speak for themselves.
They really do. The older single entropy methods, they kind of topped out around 85, maybe 89% accuracy on a good day. But this joint entropy method, combining PE and DE, it boosted the classification accuracy to around 98%.
98%. That's practically solving the problem, especially when you remember we're talking about noisy, short data sets. How well did it hold up under those really tough conditions?
That's the other impressive part. The methods are inherently robust because looking at relative order like PE does or overall distribution like DE does is just less sensitive to that spiky, random, short-term noise than the old geometric methods were. They're designed to see the forest for the trees, to capture the aggregate structure. So the high accuracy holds up remarkably well, even when the data isn't perfect.
Okay, let's pivot now to that other stream of research. The group that said, okay, entropy is great, but maybe it's just a middleman. Let's try to build features directly from the abstract concepts of complexity theory itself.
A really bold and interesting approach. They wanted to prove that the magic wasn't in the specific math of entropy, but in the power of the underlying ideas. So they went straight to the source: emergence, self-organization, and complexity. And they tried to create their own direct mathematical definitions for them.
I mean, how do you even do that? How do you write an equation for something as philosophical as emergence?
Well, their definition for emergent behavior was really clever. They defined it as the measurable difference in information content between the system's input, so its current state, and its output, the next state you observe.
So how much new information is the system generating at each time step?
That's it. If the next step is completely predictable from the last one, emergence is 0. If the system is constantly surprising you, generating novelty, then emergence is high.
Okay, that makes sense. What about self-organization?
For self-organization, they looked at the overall statistical distribution of the signal's values. They basically measured how far that distribution was from a perfectly uniform distribution, which is the state of maximum randomness or maximum entropy.
So a highly organized system will have a very non-uniform structured distribution.
Right, even a chaotic one. It prefers to visit certain states far more often than others. It has a statistical footprint. And then for their main feature, complexity, they just defined it as the product of the other two.
Emergence multiplied by self-organization.
Exactly. Their argument was that to be truly complex, a system needs both. It needs a high degree of internal order and a high degree of novelty generation. A crystal is organized, but not emergent. Gas in a box is emergent, but not organized. Chaos has both.
And they added one more feature to the mix for predictability.
They did. They used the Hurst exponent. This is a really crucial measure. The Hurst exponent is all about gauging a signal's long-term memory or persistence.
So what does its value actually tell you?
Well, a Hurst exponent right around 0.5 means the signal is basically a random walk, no memory, like a coin flip. What happened in the past tells you nothing about the future. If the value is below 0.5, the signal is anti-persistent. An up move is slightly more likely to be followed by a down move. It tends to revert to its mean.
Like we see in some financial markets.
Precisely. And if the Hurst exponent is above 0.5, the signal is persistent. An up move is more likely to be followed by another up move. It has a trend. This indicates long-term dependence, which is a classic signature of a complex or chaotic system.
So this team took the Lorenz system, generated a bunch of chaotic and random data, and then for each signal, they calculated these 4 conceptual features: complexity, emergence, self-organization, and predictability via the Hurst exponent.
And they fed that feature set into standard machine learning models, things like a random forest classifier.
And the result?
It worked incredibly well. This direct, concept-driven approach achieved an accuracy of around 92% on their test data.
Which, okay, it's not the 98% from the Joint-Entropy team, but 92% is still a massive success. It proves the point.
It completely validates the theoretical foundation. It shows that the core concepts are what's doing the heavy lifting, regardless of whether you measure them with entropy or with these direct definitions.
And did they check which of their features was most important?
They did, and the model's feature importance ranking was the final confirmation. It showed that complexity, emergent behavior, and self-organization were by far the most powerful discriminators. It's just a beautiful reinforcement of the idea that if you can successfully translate deep theory into practical metrics, you get powerful results.
Okay, so we have 2 different highly successful theory-driven, data-based approaches that have, in large part, solved this decades-old problem. If we can get between 92 and 98% accuracy, why didn't the research just stop there? What is the one single unavoidable limitation of both of these brilliant methods?
The limitation is baked into their design. It's the act of data summarization.
The compression.
The compression, exactly. Both of these methods take a long sequence of data, maybe 1,000 data points that represent the signal's history, and they distill that entire rich history down into just 2 or 4 characteristic numbers.
We're back to the 4-word movie summary problem. Exciting action, happy ending.
It's exactly that. You get the gist. You get a powerful, accurate gist, but you have fundamentally discarded the signal's microstructure.
All a nuance.
All the nuance, the subtle temporal ordering, the fine-grained patterns that pop up and disappear over very short timescales, all of that is lost in the average.
And in these really high-stakes, real-time environments, that microstructure could be the most important part of the story.
It could be everything. Let's go back to the power grid. Knowing the general complexity of the wind output over the last hour is great for setting that big spinning reserve buffer.
The macro strategy.
Right. But if you want to prevent a localized cascade failure that's about to happen in the next 5 seconds, you need to understand the instantaneous, fine-grained pattern of that fluctuation right now. And that's the microstructure that got thrown away when you compress the signal down to 4 numbers.
This feels like it leads to a much bigger conceptual shift, one that goes way beyond just chaos theory. For decades, the entire field of signal processing was basically about one thing.
Filtering.
Filtering out the noise to get to the clean signal.
And the profound lesson from all of this work in complexity theory is that you have to stop discarding the noise. What looks like noise is not just interference to be thrown away. It is the intricate fingerprint of the system's underlying deterministic nature. You have to learn to listen to its structure.
The most important part of the story might be hidden in what we used to call static.
That's the paradigm shift. And that realization that the microstructure is critical is what drives the entire field directly towards deep learning.
Because if manual feature engineering, even this brilliant theory-driven feature engineering, inherently requires summarization,
then the next logical question is, can we train a deep neural network to look at the raw high-resolution data and learn to automatically discover and extract these concepts, emergence, self-organization, complexity on its own, without losing that crucial temporal detail?
Can we build a machine that learns the features for us?
That's the question. But the ultimate ambition is actually a step beyond that. Can we design a neural network architecture that doesn't just learn these features, but whose very structure is inspired by or even constrained by these theoretical concepts?
So you're not just using the theory to create the input data for the model. You're trying to build the theory into the wiring of the model itself.
Imagine having a layer in your network that is specifically designed to measure order preservation, like permutation entropy, or a custom loss function that actively penalizes the model if its predictions stray too far from the geometry of a known strange attractor.
That's a whole other level. That's moving from theory-driven feature engineering to theory-integrated model architecture.
It's a massive transition, and it's where the cutting edge of this research is headed.
What a landscape.
Okay.
Okay, let's just quickly run through the ground we've covered in this deep dive. We started by defining deterministic chaos, this paradox of a system that is rule-based but practically unpredictable, all driven by the butterfly effect.
We then established why this distinction from random noise is absolutely vital, with huge operational stakes in medicine. The gentle nudge versus the massive shock and an energy, where it determines millions in operational costs.
We track the paradigm shift away from those classical model-based tools like Lyapunov exponents that were just too brittle for real-world noisy data, and towards these much more robust, data-driven methods.
And we really dissected the 2 winning strategies. First, the Joint-Entropy method, hitting that phenomenal 98% accuracy by using 2 complementary lenses, PE for self-organization and DE for emergence, to pull the signals apart in feature space.
And then the direct feature engineering method, which hit a strong 92% accuracy by building its features directly from the abstract concepts of complexity theory, proving that the theory itself was the key.
But, and this is the crucial caveat, we identified the inherent limitation of both. They rely on summarizing data, which means they lose that fine-grained microstructure, the very thing you might need for real-time control.
Which pushes the whole field into the arms of deep learning. And that brings us to our final provocation for you to think about. When we finally succeed in designing a deep neural network that can automatically learn these complex dynamics, self-organization, emergence from raw data, what have we actually built?
Are we just creating a better performing black box, a tool that just gives us a higher accuracy score on our test set?
Or is something deeper happening? Could the very act of successfully designing that architecture, a machine whose internal structure has to, in some way, mirror the dynamics of the physical system it's modeling, be a form of scientific discovery itself?
Could the final optimized architecture of that neural network become a new kind of theory? One that reveals fundamental truths about the system's physics that we couldn't see with our traditional equations. That's the ultimate question at the intersection of AI and fundamental science. Something to think about until next time. Welcome back. Today, we are undertaking what I think is a really critical mission.
Okay.
We're analyzing the newest blueprint for an artificial intelligence that can correctly classify the actual, the fingerprint of a complex system.
Right.
And this isn't just another jump in computational power. This feels like the definitive moment where we're successfully bridging that gap between complexity theory, the pure understanding of how these messy systems work.
And deep learning.
And deep learning, exactly. The computational muscle we need to actually interact with them in real time.
Exactly. This deep dive is, well, it's essentially part 3 of a conceptual journey we've been on for a while now. We're moving from why this is necessary to the actual solution.
Right.
If you remember our previous sources, we really established the need for this kind of AI brain.
We did. We talked about the smart grid.
Smart grid, high-frequency trading, medical monitoring, all of these operate as a complex adaptive system, or a CAS.
And these are systems defined by those highly nonlinear interactions, the feedback loops, and I think this is the crucial part, the emergent behavior that you just can't predict with old-school linear models.
You can't. That was our philosophical grounding, our starting point.
And then from there, we drove home what is really a central life-or-death operational problem. In these high-stakes CAS environments, energy, finance, and especially medicine, correctly distinguishing genuine deterministic chaos from purely random structureless noise is the fundamental first step for any kind of effective control.
We spent a lot of time on that. The idea that mistaking one for the other is operationally catastrophic.
Absolutely.
And that context, that whole setup, leads us directly to the technical challenge we're tackling today.
Which is what, exactly?
It's that the past data-driven methods for actually classifying chaos, they hit a wall. Absolute ceiling in their accuracy.
Because they were relying on manual feature engineering?
Heavy, time-consuming manual feature engineering. And look, it was smart stuff, but it suffered from a fundamental, just an unavoidable flaw, information loss.
So you're taking a massive, rich data set.
Right. And you're compressing it into just a handful of summary statistics. And in doing that, you discard the subtle temporal ordering, the fine-grained microstructure that the system is actually hiding.
Okay, so we knew the theory about the nature of chaos was sound, but our implementation of it through that data summary was just flawed.
Deeply flawed.
And that's where today's source material comes in. We're diving into a technical paper. It's from the International Journal of Engineering, and it proposes a complete conceptual reversal.
It really does. They solve this information loss problem by integrating the core insights of complexity theory. Specifically, this idea that the crucial information is sparse.
Right.
And they build that idea directly into the physical architecture of a deep neural network.
This is the nexus point we've been searching for. So instead of summarizing the data and then trying to classify it,
they're feeding the raw data into a machine that is architecturally constrained. It's forced to seek those sparse, theoretically relevant features.
It's like building the theory right into the machine's wiring.
That's a great way to put it. And by doing that, the network was able to solve this incredibly difficult classification problem with just stunning efficiency.
And the final outcome is the ultimate validation, right?
Oh, absolutely. The network achieved a staggering 99.45% classification accuracy on the famous Lorenz system.
Which, for anyone who's not familiar, that's the textbook canonical example of a chaotic system. It's the one everyone starts with.
It is. And that near-perfect performance, it demonstrates the profound power of this theory-integrated design. And that's what we need to break down step by step today.
We have to understand not just the result, but the actual mechanism that made it possible.
It really does set a new gold standard. And I think more importantly, it unlocks control strategies that were, well, they were basically impossible before this.
Okay, so before we get into the technical brilliance that led to that 99.45% number, let's take a deep breath. Let's firmly establish why this leap in accuracy isn't just some incremental academic footnote.
It's not?
This is a change that fundamentally alters operational capability in fields where mistakes cost lives or, billions of dollars.
It all comes down to the stakes. It's about differentiating deterministic chaos from pure noise.
Right.
And if you, the listener, take away just one thing from this part, it should be the difference in how you respond operationally.
So chaos, as we've talked about, it's deterministic.
It follows incredibly strict but often nonlinear mathematical rules. Now, its long-term future is profoundly unpredictable because of that extreme sensitivity to initial conditions.
The butterfly effect.
The butterfly effect. But, and this is the key, it has a hidden structure. Physicists call it the strange attractor, which means its short-term behavior has a memory. It's not random.
Whereas noise is the complete opposite of that. It is pure randomness. I love the coin flip analogy.
It's perfect. The last 100 flips tell you absolutely nothing about what the 101st flip is going to be.
No memory, no internal structure.
No strange attractor to guide it, nothing.
And mistaking one for the other dictates whether your control strategy is brilliant or just utterly destructive.
Let's go back to that visceral example we used before. The medical world, and specifically cardiac arrhythmia.
Okay, so if a heart rhythm, let's say the signal that leads up to ventricular fibrillation is mistaken for random noise, for pure randomness, what's your only option? What intervention are you left with?
You're left with the brute force response. You have to assume the system is too random, too far gone to steer it gently.
So you need the paddles.
You need the high-energy defibrillation, the lightning bolt approach. It's essentially a massive electromagnetic system reset. You momentarily stop the heart's electrical activity in the hope, and it is a hope, that it will restart in a stable, healthy, non-chaotic state.
It's traumatic, it's energy intensive, and it's all based on an assumption.
A dangerous assumption. But the research now suggests that, very often, these pre-fibrillation states are not random noise at all. They're highly complex, deterministic chaos.
So what does a correct diagnosis unlock?
It unlocks incredibly delicate, intelligent control. Because the system is deterministic and because its defining characteristic is that exquisite sensitivity to initial conditions, you can actually exploit that sensitivity.
You can use its own nature against it.
Precisely. Researchers have developed these techniques that use what are called pulse parameter modulations, tiny, carefully timed electrical flicks. They often require just a fraction of the energy of full defibrillation shock.
That's the gentle nudge we talked about.
That's the gentle nudge. That small, carefully timed pulse is then amplified by the system's own chaotic dynamics.
It's like kicking a marble at the top of a mountain.
That's a perfect analogy. You don't need much force to send it down a dramatically different path.
Yeah.
You nudge the system off that strange attractor, and you guide it back toward a stable, healthy rhythm.
So the quality of the diagnosis literally determines whether the treatment is traumatic and assumption-driven or intelligent and optimized.
And suddenly that 99.45% accuracy has massive real-world implications.
Okay, let's shift from lives to dollars. The economic consequences in the energy sector, which is the immediate context for the smart grid. Let's talk about forecasting output from a huge multi-megawatt wind farm.
Right. Wind farm output is inherently spiky. It's erratic, and sometimes it's highly chaotic, just depending on the atmospheric turbulence.
So if a utility company assumes that all those high-frequency fluctuations are just purely random noise, their hands are tied.
Completely tied.
Yeah.
They have no short-term predictive capability beyond just looking at simple averages.
And because they can't predict the next few minutes with any confidence, they have to build this massive conservative buffer into their operations. This is the concept of spinning reserve, right?
Absolutely. Spinning reserve means the utility has to keep massive backup power plants, often just running idle burning natural gas, for instance.
Just wait.
Just waiting to instantly compensate for an unexpected drop in wind generation. If you have, say, 500 megawatts of wind power online, you might be required by the grid operator to keep 100 megawatts, maybe 20% of your capacity, running hot as reserve.
That is hugely expensive. That fuel, the maintenance, that costs the utility millions, maybe hundreds of millions every single year.
It's capital waste, and it's driven by ignorance. It's driven by the assumption of randomness.
Good.
But if the system can correctly classify the wind farm's output as deterministic chaos, that changes everything. It means there is a hidden structure, there's a finite memory within that time series.
The system's current state actually contains meaningful, exploitable information about where it's going to be in the next few minutes.
Right. Short-term prediction, while you'll never get long-term certainty, it suddenly becomes achievable.
And if you can trust that short-term forecast, even for just a 5 or 10 minute window ahead, the requirement for that safety buffer just plummets.
They can slash it. Instead of a 20% conservative buffer, maybe they operate with 5 or 10%. And that reduction in spinning reserve translates directly into massive savings, much better grid efficiency, and, reduced emissions.
So the difference between classifying it as noise or chaos is the difference between millions lost or millions saved.
The accuracy gain isn't academic, it's fundamental to modern operational capability.
Okay, the necessity is firmly established. Now, let's look at why, despite decades of research and these massive stakes, achieving high accuracy was so historically difficult. We need to detail the failures of the prior classification methods.
Right, there were really two major categories of failure, and both of them, interestingly, were informed by the complexity science community. First, you had the classical model-based tools.
So this is things like Lyapunov exponents, fractal dimensions.
Exactly. And these were beautiful concepts mathematically. They relied on measuring the system's geometry in phase space, literally trying to map out the shape of that strange attractor.
Can you just briefly remind our listener what specifically a Lyapunov exponent is measuring?
Sure. It measures the average rate of exponential divergence between two infinitesimally close trajectories within the system. So you start two identical systems side by side, with just the tiniest difference in their starting points, and you measure how quickly their paths fly apart.
So if that rate, the exponent, is positive?
You have chaos. If it's negative, you have stability. It seems like the perfect mathematical definition.
It sounds like it should be the perfect tool. So why did these methods fail so badly in the real world?
They failed because they were fatally brittle. The math you need to accurately derive that exponent requires incredibly clean, long time series data. The moment you introduce real-world contamination,
Sensor noise, environmental interference.
background power fluctuations, anything, it introduces these non-deterministic, high-frequency spikes. And those spikes completely swamp the delicate geometric calculations you need to find the average long-term divergence rate.
So they worked brilliantly on perfect, simulated data from a computer.
But they were totally useless for a real wind turbine or a real cardiac monitor.
So that failure of the model-based tools, it forced a shift in thinking. Researchers stopped trying to reverse engineer the perfect mathematical model and started looking for the system's fingerprint directly in the data itself.
Right. This led to the first data-driven attempts using manual feature extraction.
And this was a philosophical shift.
It was. Researchers used their deep knowledge of complexity theory to inform which features they even looked for. They identified these core characteristics they believed were crucial discriminators: emergence, predictability, self-organization, overall complexity.
And then they built metrics to try and quantify those things, like the Hurst exponent for predictability or disequilibrium for self-organization.
Exactly.
Now, that approach seems philosophically validated, right? I mean, if you can find metrics that measure the unique characteristics of chaos, shouldn't that work?
It proved that the theory was right. Those characteristics are the crucial discriminators. But the methodology suffered from that fatal flaw we mentioned earlier, the information loss problem.
Let's really drill down on this, the data compression.
Okay, imagine you collect a high-resolution time series from a sensor. Let's say it's 20,000 instantaneous voltage or velocity measurements. It's a deep, continuous record of the system's pulse over a few minutes.
Okay.
That data, that 20,000-point signal, contains all this rich, fine-grained detail about the system's instantaneous fluctuations. The manual feature approach took that entire 20,000-point record and compressed it down to just a few summary statistics, maybe 4 or 5, or if you're lucky, 10 numbers in total.
The analogy of summarizing a 20,000-word novel with 4 words doesn't even do it justice.
It doesn't. You're not just losing the microstructure. You are deliberately discarding the subtle temporal ordering that you need for real-time control.
And the consequence of that mandatory information loss was
hard performance ceiling. These early attempts, when you fed those few features into general, shallow classifiers like support vector machines or simple decision trees, they consistently topped out. They hovered around 77% accuracy.
better than nothing, better than the brittle models. But 77% is not reliable enough to deploy.
Not for a power grid, not for a human heart. No way.
Okay, this brings us to a really crucial point in the story of this research. Before we jump straight to deep learning, there was an important refinement that happened, one that proved the theoretical potency of these complexity features, even while it was still limited by the methodology.
Yes, the joint-entropy approach. This paper was so crucial because it proved that the problem wasn't the features themselves, but how they were being combined and extracted.
So what did they do differently?
They achieved a massive breakthrough by carefully selecting complementary features. features that measure different aspects of the underlying dynamics, which minimize the mathematical correlation between them.
Can you ground that for me with the specific metrics they chose? What were the most complementary features they found?
Certainly. They focused heavily on two metrics that came from information theory. First, something called permutation entropy, or PE.
Okay, what does that measure?
It quantifies the local self-organization, the complexity of local transition patterns in the time series. So essentially, it measures how often small-scale sequences of ups and downs repeat or change.
So that's the local micro-level order. What was the second one?
The second was distribution entropy, or DE. This measures the complexity and the global distribution of the values, how the strange attractor fills up its space. This is a measure of emergence.
So by combining PE, which is local order and self-organization, and DE, which is global complexity and emergence, they found a kind of statistical sweet spot.
Exactly. When they calculated these two metrics for a bunch of chaotic systems versus noise, they created a scatter plot. And on that plot, the clusters of chaotic and noisy signals, which had previously overlapped heavily when you only used one feature, were now cleanly pulled apart.
And the performance boost from this was?
It was a breakthrough. That refinement, using just 2 or 3 carefully calculated features fed into a standard random forest classifier, achieved an accuracy of up to 98%.
Wow.
It was huge. It proved definitively. The theoretical foundation of using complexity features is potent. It works.
But there's still a but.
There's still a but. They achieved 98% accuracy on classifying the system type, but they had still thrown away the fine-grained, instantaneous microstructure of that original 20,000-point signal.
They solved the classification problem for diagnosis, but they hadn't given a controller the real-time, high-resolution data it needs for effective control.
Exactly.
So to recap, 77% proved that the compression was the problem. 98% proved that the theory was right. And now we move to the focus of this deep dive. The solution that retains the theoretical grounding but solves the data compression and information loss problem entirely.
This is where that IJEE paper from 2023 finally steps in. The researchers recognized that the key to moving beyond that 98% plateau and to getting to real-time operational capability was twofold.
Okay.
First, they had to allow the model to ingest the raw, high-dimensional 20,000-point data directly, eliminating all manual feature extraction.
Get rid of the compression.
Get rid of the compression.
Yeah.
And second, they couldn't just throw that massive amount of data at a blind black box network. They had to integrate the wisdom of complexity theory into the machine's actual structure.
And they took that conceptual leap, which was informed by the success of the Joint-Entropy paper. They call it sparsification.
Yes. The core insight, remember, is that you can classify chaotic time series using only a few key complex system features: emergence, predictability, and so on.
So if only a small set of features are truly relevant.
Then the optimal output vector that the machine learns should be what we call sparse.
Wait, hold on. You're saying the signature of chaos is simple, even though the system that generates it is incredibly complex.
Yeah.
That feels really counterintuitive. How is that possible?
It is counterintuitive, but it's mathematically sound. The complexity is in the process of generation, all the nonlinear dynamics. But the characteristics that differentiate that process from pure noise are actually few and distinct.
Can you give me an analogy?
Think of a fingerprint. The human body is infinitely complex, but its identity can be captured by the sparse set of minutia points on your fingertip.
Okay, I see.
Similarly, the essential distinguishing information of a chaotic system is concentrated in only a few dimensions of its feature space. The rest is just irrelevant noise or redundancy.
Okay, so the mission became design a deep neural network whose architecture actively enforces this sparsity constraint, rather than just letting the feature learning happen blindly inside some black box.
Precisely. They started with a base architecture, which was a fully convolutional network, an FCN.
And that's a good starting point for time series data.
It's the optimal starting point. An FCN is designed to treat the 1D time series signal, much like a normal convolutional network treats a 2D image.
So instead of looking for edges and corners in a picture, the convolutional filters are sliding along the time series, looking for local patterns.
Exactly. They're looking for what you could call motifs, local, recurring patterns, or specific short sequences of upswings and downswings that might indicate a local transition structure. The FCN automatically learns thousands of these potential motifs across different scales.
But the problem is, many of those initial motifs probably just correspond to noise or sensor jitters or highly redundant information.
A huge number of them do. And this is where the architectural innovation comes in. This is how they translate the concept of sparse complexity into the actual mechanism of the model.
What did they do?
It was a very specific and I think very deliberate tweak to the FCN's feature extraction block. They inserted 2 max pooling layers between the 1D convolutional layers, not just at the end, which is standard.
In the middle.
In the middle. This is the critical theory integrated step.
Let's detail the function of those max pooling layers in this specific context. This is more than just simple downsampling, right?
Oh, it's far more. Max pooling works by taking the maximum value within a little window of a feature map, and it effectively discards all the other values in that window.
Okay.
In a standard FCN, you often use pooling just at the end to prepare for classification. But here, by placing 2 layers intermediately, the authors enforced a sequential, aggressive form of feature selection.
So they are forcing the network to immediately discard the low magnitude or insignificant features, which should be the noise, and to keep only the high magnitude, strongest signals, which theory suggests should be the core, sparse features.
It is pruning with intent. The paper explicitly stated that the layers were there to prune redundant or insignificant features at each stage and to progressively reduce the dimensions.
So this mechanism is the physical manifestation of that sparsification hypothesis.
It is. They are forcing the machine to concentrate the essential information into a smaller, more meaningful latent space.
I can see how this helps the theory, but let's talk about the practical benefits. These are crucial for any real-time system.
The primary practical benefit is efficiency in deployment. Now, this architecturally constrained model, it actually took slightly longer to train to convergence than a standard FCN.
Why is that?
Because it has to satisfy that extra constraint. But the dimension reduction that's enforced by those intermediate pooling layers led to a significantly faster evaluation time during classification.
And that's critical. When you put this AI on the smart grid to classify a voltage fluctuation in milliseconds, or in the ER to classify a heart rhythm instantaneously, a faster runtime means the difference between proactive control and a late reaction.
Exactly. Speed and efficiency are built right into the structure of the intelligence itself, because it's no longer processing 20,000 points of raw data. It's classifying based on the handful of sparse, high-quality features it was forced to concentrate.
Let's talk about the scale of the implementation and the raw data. This is where we really see the difference from that old 77% method, which condensed 20,000 points into 4 numbers.
The model was tested on a very robust data set, 10,000 distinct samples, all generated from the classic Lorenz system.
The prototypical strain detractor.
Right, and the samples were meticulously labeled based on the known math. The system is chaotic if a certain parameter, ρ, is greater than 24.74. That parameter controls the bifurcation point, so the researchers could generate both chaotic and non-chaotic signals under very controlled conditions.
And crucially, the high-dimensional input was the entire signal.
Yes. The model took the raw time series data directly. Each sample was a feature vector of 20,000 data points.
The whole 20,000-word novel fed whole.
Exactly. But now the AI has the ability to learn where the 3 most important sentences are, rather than having to reread the whole thing every single time. They completely circumvented the information loss problem.
And that high input dimensionality means the role of those intermediate pooling layers becomes even more vital.
Yeah.
Did they find that the size of those pruning layers, the level of sparsification actually mattered?
It mattered profoundly. They did extensive hyperparameter tuning, specifically on the pooling sizes, which they called K1 and K2. And they show that you can't just blindly prune. You have to find that sweet spot for the theoretical insight to pay off.
What happened if the reduction was too aggressive, too early?
If the sparsification was too aggressive, say if they pooled down to only 50 features right away, the performance degraded significantly, sometimes by 10% or more.
Interesting.
This proves that even in chaotic systems, the crucial features are not immediately obvious. The convolutional layers need some time to process the 20,000 raw points, identify the initial candidate motifs, and then the pooling layers can begin the structured theoretical pruning process.
So it's a careful ballet of discovery and then refinement.
Exactly. The optimal pool sizes were found to be a K1 of 20 and a K2 of 10. And this just indicates the importance of carefully balancing that reduction process to make sure the essential defining features of the strain detractor's dynamic are concentrated, not discarded prematurely. It validates the whole approach.
All right, let's get to the dramatic, conclusive results that validate this entire approach. The performance leap is the ultimate payoff for merging complexity theory and deep learning architecture.
The proposed deep learning model, that FCN, with the intermediate sparsification layers, it achieved an unparalleled classification accuracy of 99.45% on the unseen test data.
That is nearly indistinguishable from perfection, especially in a field where, 77% was considered the ceiling for these data-driven methods?
It's hugely.
Let's put that 99.45% in context. Let's compare it directly to the progression of research we've detailed.
Okay, we can trace the whole scientific journey. It's significantly higher than those first data-driven attempts that suffered from heavy information loss. Those plateaued around 77%.
Check.
It definitively surpasses that critical refinement we discussed, the joint-entropy approach, which required heavy manual selection of features and achieved 98%.
And while 98% validated the theory of sparse features,
0.99.45% validated the superiority of the deep learning methodology to extract those features without any loss.
and crucially, it even edged out standard, powerful deep learning models that didn't have this specific architectural constraint. The difference here is the proof that integrating the theory really matters.
Absolutely. A standard FCN architecture, if you run it without the specific intermediate pooling, without that dimension reduction constraint, it achieved a very respectable 99.2%.
Still very high.
Very high. A deep multi-layer perceptron, an MLP, achieved 97.25%. That small but measurable 0.25% gain by enforcing the sparsification constraint, that proves the hypothesis. The architectural design, consciously inspired by the underlying theory of complexity, it provided a real, quantifiable edge in classification performance.
The conclusion is undeniable, then. By translating that abstract theoretical understanding of complexity, the idea that the crucial information is sparse directly into the physical constraints of the neural network's architecture, the model overcame the limitations of information loss and achieved near-perfect classification.
It demonstrated a true synergy between complexity theory and advanced computation.
Okay, so let's synthesize this entire conceptual journey for the listener. We moved from the theoretical failure of classical model-based methods like the Lyapunov exponent.
Which were just too brittle for noisy real-world data.
Then we went to the limited but philosophically crucial success of the first manual feature extraction attempts.
Which proved the necessity of thinking in terms of complexity characteristics, but hit that hard 77% ceiling because of data compression.
Then came the brilliant refinement of the joint-entropy approach,
Which proved the potency of those specific characteristic permutation and distribution entropy hitting 98% accuracy, but it still required heavy manual effort and it still suffered from data loss.
And finally, we arrived here at the theory-integrated deep learning solution, which automated the feature extraction, overcame the compression loss by taking the full 20,000-point signal, and achieved 99.45% accuracy and faster runtime efficiency.
So the core takeaway, I think, for anyone who's trying to navigate a complex system is this. Leveraging the specific characteristics of complexity emergence, self-organization, predictability. That is the key ingredient for solving this difficult classification problem.
The machine is learning to read the system's fingerprint with near-perfect reliability.
And that moves us past just passive observation.
And this success confirms one of the most profound conceptual leaps in this field, which is that a complex adaptive system's macro behavior.
So system stability and impending collapse, a healthy cardiac state.
Right. All of that leaves a measurable, quantifiable signature on its micro-level time series data. The micro dictates the macro.
The system is always whispering what it's about to do. You just have to know how to listen. And, crucially, you have to have an intelligent architecture that can isolate that sparse, defining whisper from all the background noise.
And the practical implication for fields like power engineering or medical devices is just immense. If we can now accurately classify chaos in a power grid or a heart rhythm with 99.45% accuracy, we have completed the prerequisite step for effective nonlinear control.
We can confidently choose the gentle nudge over the lightning bolt.
Every time.
This high accuracy is the absolute foundation. It allows us to move from merely observing and documenting complexity to actively managing and steering it. This architecture provides the platform upon which proactive, low-energy, nonlinear controllers can finally be built.
Which leads us to the final provocative thought, the ultimate goal that's implied by all of this foundational research.
Okay.
We've established that the complex system's macro behavior leaves a recognizable, quantifiable signature, a sparse fingerprint on its micro-level time series data.
The fingerprint of a collapse is quantifiable in the voltage spikes minutes before it happens. We can see it coming.
So the ultimate challenge for the next generation of AI control systems is the inverse. Can we reverse the process?
What do you mean?
Instead of just reacting to the complexity we observe, instead of just reading the fingerprint, can we use the AI to identify those emergent features in the time series and use them as targets for fast-acting, nonlinear controllers to actually engineer those features?
You mean taking control of the self-organization itself. So if the permutation entropy is too low, indicating the system lacks adaptability, can the AI issue a control signal that's specifically designed to raise the permutation entropy to a more resilient level?
Exactly. Can we deliberately structure the micro-level complexity and the self-organization of the signal? By adjusting the system's parameters, like temporary load or voltage distribution in a grid, can we purposefully induce desired macro-level emergent behaviors?
Like ultra-resilience or robust self-healing?
Or high efficiency, right, within the overall complex system?
That is a huge conceptual leap. That's moving from prediction to creation. The ultimate role of the AI brain isn't just to observe chaos, but to become a masterful conductor of complexity.
Actively engineering reliable, desired order into the system.
By tuning the characteristics of the signal itself.
A truly mind-boggling prospect for the future of infrastructure and control. Thank you for joining us for this deep dive into the blueprint for controlling chaos.
My pleasure.
We'll catch you next time. Welcome. Today, we are taking a fascinating stack of research that really moves from these deep philosophical concepts right into practical AI implementation.
That's a great set of sources.
Our mission here is to synthesize these into a clear blueprint. We want to explain the intellectual leap you have to make to build a functional AI brain for our next generation of infrastructure.
And that's absolutely essential. I mean, when you look at the challenge of modernizing something as vast and critical as the electrical grid, you realize pretty quickly you just can't rely on the old rule book.
Right.
The core challenge is, well, it's moving beyond simple mechanical physics to managing a dynamic, almost you could say a living ecosystem.
And managing an ecosystem requires completely different tools than managing a machine. So we're going to connect the massive philosophical challenge of building the smart grid directly to the breakthrough statistical methods used to actually diagnose its data. This deep dive is your roadmap. It's for seeing precisely how chaos theory and complexity science directly inform the design of reliable next-generation AI.
Let's start with that foundational pivot, because if you misdiagnose the system, you will inevitably build the wrong kind of AI to control it.
Okay, so for over a century, the traditional electrical grid was, it was a marvel of deterministic, centralized engineering.
Absolutely. Power flowed in one direction, from these giant generation plants out to passive consumers.
Then you can model the whole thing with highly predictable, linear physics equations.
The smart grid just flips that model on its head. It's a dense two-way street where you have decentralized generation from solar and wind. You have active consumers responding dynamically.
So it's not just physics anymore.
It's not. It's a socio-technical system.
So we have to use the official term, a complex adaptive system, or CAS. But why is that specific label CAS so crucial? Why not just call it a complicated system? A jumbo jet is complicated, but we fly those safely every day.
That's the key difference. A jumbo jet is complicated, but it is, at its heart, linear and mechanical.
Yeah.
If an engine loses 50% thrust, the plane loses, roughly 50% of its capability from that engine. The effects are localized and predictable.
Okay.
A CAS, however, is defined by nonlinear interactions.
Meaning proportionality just breaks down.
Exactly. Complexity isn't about counting the number of parts. It's about the nonlinear interactions, where a tiny cause can have a massive, disproportionate, and often unpredictable emergent effect. The system is constantly adapting.
And those adaptations feed back into the system, changing its global behavior.
That's right.
That sounds terrifying in the context of critical infrastructure. What does that emergent behavior actually look like on the ground?
It looks like cascading failure. We've seen this time and again in major blackouts. A small voltage fluctuation, maybe less than 1%, in a localized area starts a chain reaction.
And because of the way the system is designed?
Because of how the protection relays interact nonlinearly, that small flicker can destabilize the frequency across a massive region. No single component failed 100%. The disaster just emerged spontaneously from the network's own rules.
The famous analogy, conspiracy without a conspirator, no one planned the collapse. The system simply orchestrated itself.
But the hopeful inverse of emergent failure is self-organization, right? Like a murmuration of starlings moving fluidly without a central leader.
And if the system is defined by CAS, then its data is inherently complex, dynamic, and potentially unpredictable.
And this leads directly to the core analytical challenge that our other sources tackle. You have to be able to reliably distinguish between deterministic chaos and pure, useless random noise.
For most of us, chaos just means a random mess. But in mathematics, deterministic chaos is a kind of paradox. Can you break down what it means for a system to be chaotic but still deterministic?
Okay, so deterministic means the system is governed by fixed, rigid, non-random rules. If you could measure its initial state with, like, infinite precision, you could theoretically predict its entire future.
But there's always a but.
The caveat is the butterfly effect.
Yeah.
Extreme sensitivity to those initial conditions.
So the tiniest rounding error in our measurement grows exponentially until long-term prediction becomes, for all practical purposes, impossible.
Precisely. But, and this is the critical point for control systems, chaotic behavior is still bounded. It remains confined to a specific region in phase space, what we call a strange attractor.
So there's an order to it. There's a structure, even within the chaos.
There is a geometric order to its limits, even if its path within those limits is complex. Random noise, on the other hand, has no fixed boundaries, no structure, no strange attractor. It's truly unpredictable.
And the stakes of diagnosing whether you are dealing with chaos or noise couldn't be higher, because that diagnosis determines your entire control strategy. Let's look at the example of cardiac arrhythmia from the sources.
It's a perfect illustration. It's the lightning bolt versus the gentle nudge approach.
Okay.
If a doctor mistakes the heart's erratic electrical signal for purely random noise, the standard treatment is high-energy defibrillation, a complete systemic reset, a high-states, high-energy blast.
But if they correctly diagnose that erratic signal as deterministic chaos, they know the system is still governed by rules and it's confined by an attractor.
So the intervention changes fundamentally.
Right.
They can use a tiny, precisely timed electrical pulse, a fraction of the energy, to exploit the system's sensitivity. They just nudge the system back toward a stable rhythm using its own mechanics. It's far safer and more effective.
And that diagnosis translates directly to saving millions in the energy sector.
Absolutely. Think about a wind farm. Its output is highly variable. If utilities classify those power fluctuations as truly random noise, they have zero confidence in predicting sudden drops.
Which means they have to keep backup plants running just in case.
Exactly. They maintain expensive, dirty, spinning reserve backup gas plants kept idling and burning fuel.
But if the fluctuations are chaotic, they are short-term predictable.
They are. You can model the strange attractor and forecast minutes ahead with confidence, allowing the utility to massively reduce that spinning reserve and save a fortune. The difference between chaos and noise is the difference between wasteful overinsurance and optimized efficiency.
So, historically, how did scientists try to make this diagnosis?
They tried using classical model-based tools. They were trying to reverse engineer the underlying equations using metrics like Lyapunov exponents or fractal dimensions.
And that's where they hit the wall. Why did those elegant, mathematically perfect tools fail in the real world of industrial data?
Because they were just too brittle. These calculations, they depend on identifying incredibly delicate geometric structures in the data. And real-world time series, like a voltage signal from a substation, are noisy, short, and dirty.
So the noise just overwhelms the signal.
It completely swamps the geometric calculations, making the result unreliable. The data wasn't clean enough for the math they were using.
So the field had to pivot. They moved toward robust, data-driven feature extraction. The whole paradigm shifted from trying to find the equation to just capturing the system's fingerprint.
That's the breakthrough. The insight was realizing that the fundamental concepts from CAS theory emergence, self-organization, and complexity weren't just abstract ideas.
You could quantify them.
You could quantify them and use them as powerful, robust features to tell chaos from noise.
Now, we saw in the initial efforts that when they manually crafted features based on these theoretical concepts, they only achieved moderate accuracy, something like 77%. Why did that initial attempt fall short?
Well, it confirmed the importance of the features. Emergence was repeatedly shown to be the most critical discriminator, but the process suffered from information loss.
How so?
They were boiling down, say, 20,000 data points from a high-resolution signal into just 5 or 6 summary statistics. A lot of the subtle structure was just lost in the average.
And the huge jump came from what they called the Joint-Entropy approach. This is where the concept of orthogonality becomes key. They stopped looking for single, powerful features and started looking for complementary pairs.
Yes. Orthogonality means selecting features that measure different dimensions of complexity independently. You want measures that are, minimally correlated so they capture a more complete picture.
And the pairing they chose was permutation entropy PE and distribution entropy, or DE. How do those two concepts break down the complexity?
Okay, so permutation entropy, or PE, measures structural order. It looks at the sequence of the data.
So are the neighbors predictable, that kind of thing?
Exactly. It's a strong measure of self-organization, or lack thereof. Distribution entropy, DE, on the other hand, measures the statistical spread.
The global amplitude, how wide is the range of values?
Precisely. It's a strong proxy for emergent volatility.
So if you plot those two metrics together, structural predictability on one axis and statistical spread on the other, you create a two-dimensional map.
You do. And signals that were previously jumbled together in a 77% accurate mess suddenly snapped into these distinct, clean clusters on this 2D map.
And the result was?
A massive leap in performance. 98% accuracy using standard shallow classifiers.
That's significant. It proves that clever, domain-driven feature engineering, even using manual methods, can overcome the limits of simple statistical averages.
It really does.
And the quality of these features connects directly back to the ultimate goal of deployment, the trust factor.
Right. We need to transition this brilliant diagnosis from the lab bench to the operational MLOps pipeline for tasks like predictive maintenance, where humans have to rely on the AI. Accuracy alone isn't enough.
You need robust generalization. This
Yeah.
is where we talk about the relative generalization gap, or RG. This is the metric that really governs trust, correct?
Absolutely. The RG measures overfitting. Think of a student. They might score 100 on every practice exam. That's a training data because they just memorized the answers.
And then they get a 50 on the final.
All right, they get a 50 on the final exam, the unseen data. That's a huge generalization gap.
And high feature quality, like that entropy pair that's 98% accurate, that reduces the gap.
Yes, because good features act as robust anchors. Reducing the RG is the ultimate proof that your AI is not just a genius at memorizing past failures, but an actual learner that can handle novel, unseen stress scenarios.
So that reduction in the gap is what tells an operator, okay, it is safe to deploy this AI to schedule repair crews next week.
That's the metric.
We've achieved 98% accuracy using sophisticated manual features, which is fantastic for planning. But there is a massive limitation here: summarization.
Exactly. Even when we achieve 98%, we are still discarding the signal's microstructure, the fine-grained millisecond-level patterns, and we need that microstructure for instantaneous control.
So we have to shift from weekly prediction to real-time control.
We do.
And this is where the sources move into deep learning, aiming to automate that whole feature discovery process while retaining that fine-grained microstructure.
This is the next big step. The insight from the manual approach, that the distinguishing information is sparse, only a few features like the entropy pair truly matter, that directly inspired the design of a novel deep learning architecture.
They didn't just throw a standard deep network at the data. They engineered the network to mimic the theoretical insight.
Correct. They designed a fully convolutional network, an FCN, that included specialized interleaved max pooling layers. And these layers were explicitly intended to prune redundant or insignificant features throughout the network.
So it acts like an automated filter.
It does. It's continuously stripping away noise and zeroing in on the truly sparse critical information.
So instead of a human boiling 20,000 points down to two numbers, the machine is trained to find those two critical dimensions automatically, but it does so without throwing away the microstructure.
And this theoretically inspired architecture paid off dramatically. It achieved the highest performance, 99.45% accuracy. It significantly outperformed both the standard deep networks and the 98% manual feature method. And crucially, the pruning baked into the design made the resulting model faster during evaluation, making it highly efficient for real-time deployment.
So now we have a tool that can diagnose chaos from noise with incredible speed and accuracy. But this highly accurate prediction, it has to integrate back into the human-machine system, the larger CAS framework, because the human operator is never eliminated.
This brings us back to the discussion of adaptive autonomy. The human's role changes, but they are still the ultimate decision maker. The system needs a rigorous, trustworthy way to decide When does the AI take total control, and when does it hand that control back to the human?
How is that handoff decision mathematically determined?
It's based on collecting data around what are called performance shaping factors, or PSFs. These are just situational variables that affect performance, things like storm risk, equipment age, even operator fatigue levels.
The system has to know when a human is better?
Exactly. It has to know the conditions under which human intervention is safer or more effective than machine autonomy.
And they designed this handoff protocol using the mathematical rigor of Petri nets. This is far more complex than a simple if-then statement.
A Petri net provides a mathematical proof of concept for the interaction. It uses places to represent system states, transitions for events or rules, and tokens to represent resources or necessary conditions.
Give us a concrete example of how the tokens determine the action.
Okay, imagine the transition is transfer control to human. That transition only fires or executes when the necessary tokens are present. For instance, the system might require a token confirming high storm risk and a token confirming that the measured relative generalization gap of the model has exceeded a safe threshold.
And if both tokens are present, the rule is validated.
The rule is mathematically validated, and the system hands over control.
The ultimate benefit being that you can mathematically verify before deployment that the human and the machine will not get stuck in some critical feedback loop waiting for the other to act.
It guarantees the collaboration is deadlock-free. It guarantees reliability under stress, which is paramount in critical infrastructure.
So if we synthesize this entire journey, we began by recognizing the grid is a CAS, which demands a highly accurate chaos diagnosis.
A diagnosis that is solved by leveraging CAS characteristics as features. That's the 98% via entropy.
And then finally deployed via a theoretically inspired deep learning architecture, 99.45% accuracy via sparsity. It all builds toward one unified goal.
It really does.
We've established that the system's macro behavior, whether it's about to collapse or self-organize, leaves a quantifiable signature, a structural fingerprint, on its micro-level time series data. The system is telling us what it's about to do.
So the provocative question, which is the ultimate ambition driving all this work, is the inverse of that. If we can measure emergent features, complexity, predictability in the time series with 99.45% accuracy, can we use those features as targets for active control?
Instead of merely predicting chaos, can we engineer reliable order?
Exactly. The final frontier of the AI brain is moving beyond passive observation and prediction. By using fast-acting controllers to deliberately engineer the time series at the micro level, can we purposefully induce desired macro-level emergent behaviors, things like ultra-resilience, systemic stability, or robust self-healing within the grid? That is the goal. That is the goal. Actively engineering order out of inherent complexity and chaos. Moving from observer to conductor of complexity, that is an incredible ambition. Thank you for joining us for this deep dive into complexity, chaos, and the future of industrial AI design.
We hope this synthesis provides you with a clear foundation for understanding how deep theory is translating into practical, deployable technology that manages the critical infrastructure of tomorrow. We'll catch you next time.